We are going live. We are live. Let me share my screen and dive into the topics of applications of graphing from calculus. So sharing the entire screen. Sure, let's share and see what this is about. So what I'm going to do in this video is, we're still in section 1.1. We are going to look at the different applications of functions. We did domain and range in the last class. What I'll specifically look at here is more on the graphing end. So let's take a look at these parts from 1.13 to 1.15. We're just going to go over some basics of graphing that you're interested in as you proceed in calculus. And as this series of videos, as it aims here, we want to pick an application that is of interest for us. And just to show you the concept of the power of calculus and what we can look at, here's a lot of engineering fields. There's a total of 21. I could literally take a random number generator and let's say left to right, up to down is going to be our ordering. So let's go 1 to 21. Let's see a random number. We get the number 15. So we get geological engineering. Now, this is one field I don't know hardly anything about, geological engineering. So with geological engineering, this is what we're going to do. We're going to go geological engineering, quadratic relationships, and data. So let's make this nice and big for you to see. Geological engineering, quadratic relationships, and data. Let's see, or let's say generate data, and let's see what ChatGPT does for us. And look at this. It's giving us slope stability in open pit mining. It gives us a function, maximum slope height in meters, horizontal offset from the slope toe, and we are given data. This is great. This is exactly what I want to show you, and just show you that, the geological engineering is one of the fields I have zero expertise in, except I know a lot about calculus, and it could help us understand functional forms. So we're talking about open pit mining. The stability of slope depends on a multitude of factors, including height of the slope and the horizontal distance at its base. This one's going to worry about horizontal offset from the slope toe, and we're going to have a maximum slope height. Okay, you might be a little bit puzzled by this relationship. You might not be a geological engineer, but we have the context of a problem. From my vantage point, when I was a student, I remember looking at functions and saying, where in the world do they come from, or where did they come from to begin with? A little thing here on ChatGPT, we could copy the table. And I'm going to input this in Excel. And all right, didn't come out as nicely as I might hope, but we can do some editing and manipulate it. So, this one's a little bit on the tougher side. Let's see what we could do. How about we go to, and just to show you some tricks in Excel, what we can go to, we have the data. Looks like we're rather limited on the data, unfortunately. Let me try something else. If that doesn't work nicely, how about doing things the predictable way of copying this way? I'm trying just a few different ways. You know what? Let me do this. I copied and pasted originally from Excel. Let's do something called data text to columns. And let's say fields are assigned in columns with space between each field or delimited. Let's go to next and see what we can do. It looks like they have, I don't know, they have something like this with the lines right here. I'm getting somewhere with the lines at least. So you can see the lines that I have from my data as I copy it from ChatGPT. Let's go to next, and let's go to finish and see what this produces. Well, rather disappointing. Okay, let's continue here. I say let's continue. Let's get started here. I'm going to copy and paste it right from ChatGPT in this manner and see what it produces. That looks better, actually. I wanted to copy and paste it, and I thought ChatGPT's copy and paste would do this for me, but it's actually much better just to do it manually like that. Fine. So here's my data. Offset distance versus slope height. It's got some redundant stuff there, but we'll say slope height in meters. There we go. So here's my data. And what I want to show you, one thing that's not really explained that well in a calculus book that I was always curious about is how did they take this data and really create this function? Well, what I can do is I can plot this data and see a relationship when I plot points or estimate a relationship. Now, I want to warn you, the data does not have to be perfectly fitting a functional form, but we can do our best to try to fit that form. So our graph will be, and you're actually getting a little clue here. Here's a linear fit, but the linear fit is rather lousy. So if we try to fit this by a line, we get the upward trend, sure, but not what we really wanted for a functional fit. So on the x-axis, I'm going to have slope height. Whoops, let me double check the variables again. I'm going to have offset distance and slope height. So let me do this. Offset distance. And slope height. And let me remind the viewer that this is geological engineering. Have I even spelled that right? Okay, geological engineering with quadratic relationships, great. I plotted the data, and then what I did is I went to, let me bring this up here, geological engineering. I brought this up to fit. What I'm trying to do is I'm plotting the data and I'm trying to fit the data to a functional form. So as I look at this data, it's natural to ask what is the relationship between slope height and offset distance if you're a geological engineer. I have my plot here, but a line itself is a rather poor fit for our graph. But what Excel will allow you to do, initially I had my data, but I picked the quick layout option so I can label my X and Y axis appropriately. and it came out with a function. Once you get that line, or let me also show you another way, you could also come up with a line by saying trend line. But we want to manipulate this trend line. So left click, right click, format trend line will take us to this breakdown of different functional forms. So I can change that functional form to one that I like that is perhaps a better fit. Look at polynomial of degree 2. Not a perfect fit, but pretty good. So I can put this trend line, or it's not trend line anymore, but it's a quadratic. I see the fit of the quadratic is pretty good. Sorry, I'm trying to get this to work right. The usual clunkiness with Excel. Sorry about that. Display equation on the chart. So here's the equation itself that really best fits our data. Format trend line. You can also do something called an R squared that tells you the percentage fit of your data to the curve. If I increase the polynomial order, I'm always going to get a better and better fit, but I'll lose simplicity to my function. So a key here is to understand the trade-off of if I go to first power, I just had a line which was a lousy fit. Third power fits better. Fourth power even fits better, but the functions become more and more robust and perhaps more complex and doesn't really describe and cannot really describe the relationship in words as opposed to, let's say, what a quadratic could do. As you get more terms in a function, can you reason the function reasonably? There is cubics, quadratics. There's other functions that take other forms. But for geological engineering, I'm just going to take a look at a quadratic to understand how the relationship works out. So what we did here is kind of show you how a function comes about. We fit the data to the model. So this model is a little bit different, but what Excel does, it gives you the best fit for the data for your function. This function's pretty close. It's simpler, but I might prefer, let's say, negative 0.042, 1.56, and 9.16 instead of these values. But I have the graph here, and this kind of scratches an itch that I had a lot when I was trying to learn calculus. How in the world do these functions come up to begin with? What you're doing is you're actually creating functions like this by plotting your data, and then you're fitting a curve to that data that fits those points best. So this curve, this line specifically, will give you the slowest, largest, what we call R squared, which means best fit to the curve in a quadratic form. So we're off to a great start here. We saw how I can use Excel, and you might be a complete neophyte to Excel, but I showed you how Excel can be used to illustrate the relationship of our data. So here we go with our function. Here is our graph, and it's a quadratic. It's not showing like a, with the quadratic, so many of you will be anticipating like a parabola going upwards or downwards that looks like this. This is a parabola going downwards, but it's much wider than you might have been anticipating. It's only a segment of the parabola that's valid here. Now I'm going to go back to domain and range because this model is only valid for certain values of x. So if we look back at this and say, okay, what values of x did I plug in? It seems like I can plug in values of x between 0 and 28. And my range is my output of values for my slope height. They seem to be between, let's say, 10 and 25. So the domain is the possible inputs. And I say 0. We did have some offset distance 0 in our data. So we could plug in values of 0 to 28, and we're using data from 0 to 28 to come up with our range of values, which is between 10 and 25. And one value maps to the other. It's not simply a case where if we have a small value of x, we get a bigger value of y, because at some point it turns and maximizes at about 18 for an offset distance. And we'll describe this further as we go into the description. So geological engineering, we can break down domain and range, and we see a graph from the generated data set. Here's some questions that it follows up with. Would you like a plotted graph of the relationship? I came up with a plotted graph based on the data. I reversed engineer and created a quadratic model. So I saw the differences between what was exactly a model of best fit versus the approximated one here, which wasn't quite the best fit for the data. And a different geological engineering context. Well, quite frankly, I've already seen a pretty good context here in geological engineering, and I might just say, I'm geological engineer, I'm starving for information and I need more context. Here, I'm just trying to introduce you to graphing, domain and range that we saw earlier. So with a graph, let me describe a little bit more what's going on here. With a graph, we can take a look at our domain and range and look at interpolation versus extrapolation. These are more statistical terms, but we're going to go back to our domain and note we inputted values of 0 to 28 for the offset distance. And when we input those values, this is my domain. It mapped to output values, not starting at 0, but starting at about 10 to 28. So these are the domain and range of my functions. My range for y is actually dependent on my domain for x, and in part you could say it was dependent on the minimum value that will, or they're dependent on x. It just so happens the minimum value of x maps to the minimum value of y, but that's not true for the maximum value of x and the maximum value of y. Be careful about that. This is a quadratic relationship. So with a quadratic relationship, you have a peak. So the max occurred earlier before the maximum value of the range. Now this domain and range is in a interval that we call interpolation. Use x to predict y, and let's say x and y are realistic values. If we extrapolate, we have something that is not appropriate. So it's values not appropriate in the model used in estimation. So I'm going to use mine rather than the one the book gave. Here is the model that truly fits best. Now, interpolation basically says use any value of x you want in this domain. I should do a pretty good job in estimating the relationship between offset distance and slope height. So looking at our data, we have values literally from 0 to 28, but I'm also able to say if I pick values between there, let's say if I pick a value of 12.5, x equals 12.5, estimate y. The value or the function that Excel gave you was simplified a little bit. Let me use this one. So I have negative 0.0421 times 12.5 squared. And actually, let me do this. A21 squared. So I'll put the 12.5 here. And on the right, I'm going to input the function just to show you the power of Excel, what it can do for us. I'm inputting the function 1.5571. And that'll be times A21 again, but A21 was supposed to be squared before. And then the final value, the constant value, was 9 point something. 9.1594. So I have all my xy, or I have all my values in the function. And I could see, depending on the value of x, I can predict y. So if I wanted 12, 15, and so forth, I could create a little table here. And these seem to be reasonable values in my domain. I could go further with x even. It looks like x was from 0. But the key point here is I could copy, I could put 12.5, 15, etc. And I could apply the function to all those x values and get points. And at some point, I do see the function value start to decrease. Now, this is called interpolation. If I did something like this with 40 and 50, that would be called extrapolation. But with extrapolation, you're beyond the domain, so you cannot guarantee, or you're not going to expect good results past the domain. So these are values past the domain and prone to errors. I don't know if an offset distance of 40 and 50 is physically possible, but even if it's physically possible, our model was contained between 0 and 28. So what's on the left here for repeating is interpolation, taking your data and plotting and predicting. So I could say predicting values within the domain. So when you predict values within the domain, you can expect these values to be pretty good predictors. But if you're outside the domain, don't have any expectation for anything outside the domain. These would lead to foolish results, while those within the domain should lead to pretty good results. It does depend on your R squared, but especially in calculus, a lot of the relationships follow from some scientific principle. So the predictability of y given x can be rather high sometimes. If it's too low, you might question if this function is an appropriate fit for your data. So here's a good idea when you plug in values in the domain. But if you go outside the domain, you're going to get unpredictable results. So your function can mathematically work for values outside the domain, but the intuition of our model was between 0 and 28, and we see the relationship graphically and also through the data. So through the data, it seems like it maximized about this point at about 18. So x equals 18 gives you about the maximum value of your function. I can look back at the profit function or look at what I had earlier. Now I've made this sheet rather long, but that's fine. What I've done here is I can take a look at my data or look at the graph or a data table and do my best to try to approximate where the function is maximized. And we see it's not maximized at the maximum value of x. It seems to be maximized a little bit to the right middle of the graph. Here, let's say at 18, it's about y equals 23.5. We can approximate the point from the graph where we can maximize our slope height with this given offset. Or we might be interested in other points. We might want a certain maximum height to be only 20. If we're looking for values that cause the maximum height to only be 20, you got some values on the graph at x equals 10 and 28 that will give you a slope height of 20. So there's different ways of looking at the graph and describing it. We can certainly be interested in things like this. A minimum point, a minimum seems to be at 0, 10, but a maximum is also in play. And we could also generalize the behavior increasing and decreasing, which will be interesting to us later. It tells us it's not a pure linear relationship. There's more dynamics in play. It's a downward facing parabola, but in a rather wide stance. So what I did here, just again, a reminder, I didn't take the function that the problem gave us. I said, hey, I can even do better and use this function. This is what we will call least squares. And it maximizes, or it minimizes square error. So when you minimize square error, you're getting best fit. The quadratic here fit this data very well. If I generated data that did not fit this data well, I will look at a different functional form, and we'll see different functional forms as the class continues. I came up with 2 quadratics for the first examples. Zeros of the function. There is only 1 0 of the function. It's rather predictable here. It's at the x equals 0. X equals 0, it seems like we have a y-intercept at 10. So if you're interested in zeros of the function, well, you have an intercept at about 10, or really 9 point something. The minimum point we could say is at 0, 10. but you can see the function, its intercept, when you have y equals 0, when I plug in and make a prediction, 0 squared, 0, but I'll have a 9.159, can basically say that's a 9.16. So the difference in models, one gave us a y of 10 at the minimum. This on our model, based on the fit of our graph, even goes lower than that and predicts y to be 9.16 when x equals 0. Sure, there's more things I can go with graphs, but to be honest with you, this is a great start to understand some things with where functions come from in calculus. Things I was curious about when I was in your shoes, learning calculus, and for those who might already have learned it, you get to get some additional insight on how you can use statistics to create functions. So with that being said, I am going to stop sharing, sign off. Thank you very much. Oh, end stream. Sorry, I'm yawning. No one joins as expected.